So, yeah. So, yeah. Good evening here, and good morning to Ritesh, and welcome to all of you for this the IQT lectures, which is now in a new avatar called Quantox. And Ritesh will be the first person giving the talk in this new avatar, Quantox. So I will just say by way of brief introduction about Ritesh. Maybe most of you are familiar, but Ritesh, of course, is currently a professor, as you can see from his shared slide, in the Department of Material Science and Engineering at the University of Pennsylvania in Philadelphia. So Ritesh essentially completed his undergraduate from IIT Kanpur, and then moved on to do his masters from the University of Chicago before completing his PhD from UC Berkeley, and then I think before joining Penn, he spent as a postdoctoral fellow at Harvard. So his research interests are kind of quite diverse, including structural, chemical, optical, electronic properties of low-dimensional materials, and of course also development of new probes to study complex phases of natural and engineered materials. Ritesh, of course, has has received several awards, the NSF Career Award, and the most recent one being the being elected fellow of the Optical Society of America in 2020. That is last year in the middle of this pandemic. So I think with that brief introduction, I will not take more time from Ritesh, and I look forward. No, we are quite delighted to have you here and listen to some of the exciting stuff that is going on in your lab, and in particular today, as you can see, is going to talk about using geometry and topology for designing on-chip quantum hyperentanglement photonic infrastructure. So Ritesh, it's all yours. Yeah.
Thank you, Jaydeep. Thank you, everyone, for this very kind invitation, and also to help me keep engaged in all these conversations while still being confined at home. I think we open July 1st. We will go to almost as normal mode as possible of pre-pandemic phase. So looking forward to it. But more importantly, in spite of all this hardship that we all faced, I'm really glad through this virtual mode we are able to connect and at least continue the discussion. Of course, nothing replaces meeting in person, and I still hope and want, and I've been trying to visit ISC Bangalore. Last year in March, in first week of March, I canceled my trip the day I was supposed to fly out. So, but I still hope to visit and see you all in person on your campus. I have very fond memories of ISC Bangalore, and it's last time I visited, only time I visited, I guess, was in 1996. And there's a very interesting anecdote because I had applied. I was finishing my course in Kanpur, and I had applied to University of Chicago in December. And in January there was a conference in your main building in ISC Bangalore, and some quantum chemistry something. And John Light, who was a professor in Chicago chemistry department and editor of Journal Chemical Physics, was visiting. So I met with him there, told him that I had an application pending at Chicago, and who knows, maybe it helped, maybe maybe I didn't screw up too much, and I did get an offer from Chicago, and that started my graduate journey. So so there's some very nice link that I have with Bangalore, and I want to develop more relationships, more contacts and collaborations. I'm already starting to collaborate with Jaydeep, so I'm looking forward to it. So yeah, so as Jaydeep said, research interests in my group are quite diverse, but at the core, and hopefully you will see in my talk, I'm a spectroscopist at heart. Every problem that I work on, I make it a spectroscopy problem, and that's and that's the physical chemist in me. That's my training pretty much. So it's what has changed over the years is from picking up molecular systems or liquid phase or systems and studying their dynamics using nonlinear optical spectroscopies. In recent years, in last half a decade or so, I'm picking more, you can call it more physics type problems, but yeah, crystalline systems. But the core remains the same. It's still nonlinear spectroscopies. Instead of measuring a light field out, we're measuring current. So this is what the photogalvanic spectroscopies that I'll talk about that we are developing, new variants of this. But at the core, it remains a very similar problem. Of course, in chemistry, typically in molecular systems, wave vector k is not a good quantum number. So there's a lot of teaching I had to do or learning I had to do, which I'm still undergoing. But that's pretty much the biggest change. So what I'll talk about is our efforts to we've not reached quantum yet, but it's just a vision. And 3 years back, if you had talked to me, this didn't even exist, although the vision existed in some form. And hopefully, in a few years from now, we're making good progress, but we're still not there in terms of actually making a quantum photonic infrastructure. But what we have developed as of now are some very basic devices for a chiral on-chip photonic infrastructure, and the idea is using momentum space geometry and hence topology of these certain crystalline systems or topological systems to enable this. Okay, so nothing, as you all know, nothing can happen without all the great efforts by all the PhD students. So I see Pawan is in the audience. So this is Pawan. He was in my group. I think around 2015 or so he left, and now he started at IC Bangalore. So I won't be talking about his work. I'll be talking mostly about the work spearheaded by, started by Sajal Dhara. Some of you may know him. He's in IIT Kharagpur physics. So he started this all these measurements on photogalvanic probes of crystalline systems, and then Zorun took it from there, and then I'll be mostly talking about her work. All these wonderful collaborators, Kane and Mele in physics, Andy Rapp in chemistry, and other collaborators who provided samples, all the funding agencies which fund all the effort. I mean, at least in America, I hope the system is better, but here, nothing moves without extramural funding. There's really no money internally. So you have to get money to keep your lab functioning. So I'm very thankful for all these funding agencies, NSF and DoD. That's pretty much it, which provides support. Okay, so here's the vision, which I drew many years back, but at that time I had no idea how it will happen. But the interesting thing is we have made, I think, pretty good progress. So the idea is basically borrowed from electronics and very simple photonic architectures that are used today. So in electronics, as you know, all the entire computing that we have, at least at the commercial level, is mostly done by counting the number of electrons or measuring the current that flows in the circuit. Transistors turns on and off, and these are the two states of the that we distinguish. And we do logic. We store that information in memory, in solid state drive, or whatever that we do. And the idea of spintronics, and this is making very good progress, is to encode more information in electrons, but via electron spin, which is a fundamental degree of intrinsic degree of freedom of electrons. So same thing in photonics. Photonic circuits also work by modulating the intensity of light on and off into on and off states. So can we also encode more information? Photons have more degrees of freedom. Intrinsic is photon spin, and this manifests as polarization, circular polarization, left and right circular polarization, the most fundamental polarization states of light. And also there are extrinsic degrees of freedom that one can encode in a beam of light, which is called the orbital angular momentum, where the wavefront of light undergoes this helical motion as it propagates. The polarization can be coupled or decoupled, but that's not a requirement. So it's just the wavefront of optical wavefront winds around an axis. That's the orbital angular momentum mode of light. And how many times it winds per unit time or unit distance the light travels is characterized by quantum number m, which also characterizes the topological state of light. So in order to encode more information in spin and orbital angular momentum of spin for photons, light, or photons for OM, whichever way you want to call it, you need to be able to create states. You have sources, optical sources, which produce those states with different spin and orbital angular momentum mode and coupled states. So spin orbit momentum coupled states. Then one should be able to route the signal, preferably depending on the state of the system, with minimum loss of information or power. And then at the end, you have to detect that signal, and hopefully in one shot. So this can be done. It's not that it cannot be done, but it requires a large optical table infrastructure, which is the size of a room, a lab. So integration on and making integrated devices becomes impossible. So it can be done through free space and through infrastructure that is built around where this information is being transmitted or created or encoded. So can we do this on a chip, on a microchip? So that's the question I've been asking for many years, and this is what I'll describe. But what I'm intrinsically asking is, if you want to encode, transmit, or detect signals that are related to chirality of light, because spin and orbital angular momentum mode completely characterize the chirality of light, then you cannot have regular materials or regular design structures. You have to encode chirality. You have to make the system chiral in some way, and that makes it very hard. And this is where the integration of certain symmetry states and geometry and topology of case-based geometry and topology of crystalline systems become important, and that's what I'll talk about. So the first would be very brief, because this is mostly spearheaded by my colleague Liang Feng, is the on-chip generation of these states. So what he has been working on, and we've collaborated recently, is by using principles of non-Hermitian physics. So by creating parallels or side-by-side states of system being pumped above optical gain and in loss and at the interface, and how you interface them, you can create these non-Hermitian physics type structures. So you can create Hamiltonians, which are very hard to create in electronic systems. And this is what optics allows you to do, and that's why there's a lot of interest in topological physics and non-Hermitian physics, is optical physics, is because you can create states. You can do things which you cannot do in crystalline systems, because in crystalline systems you get what you get when you grow a crystal. You can impose some constraints on top, but with light you can do a lot of things. So this is what he did, and by figuring out different ways to pump in very ingenious ways, he was able to show. I was part of this collaboration last year, that one can create on-chip lasers which can produce different spin and orbital angular momentum modes. So this is a microchip laser. So this was very promising. And very recently, this year, he published, and luckily we were collaborators, another design by using, this is again taking principles from particle physics. These are called supersymmetric, using principles of supersymmetry. Again, supersymmetry, that's an idea comes from particle physics, but in optics you can implement easily. So here he was able to extend. So people had done supersymmetric lasers, but in one dimensions. So by creating new Hamiltonians and then creating supersymmetric partners between, again, loss and gain. So what supersymmetric partners in optics allow you to do, at least that's the state of the art, is you can have, in a multi-mode structure, you can lock the frequency of lasing at precisely one frequency. So if you have a two-dimensional array, the Hamiltonian becomes more complicated. So he was able to design new Hamiltonians by creating new supersymmetric partners and create very large intensity on-chip light arrays, laser arrays, and also by manipulating this Hamiltonian, create new orbital, not new, but produce emission in different orbital angular momentum and spin angular momentum states of light. So the power was an issue from a single micro array, and now we can get much more power. So this was the advance he reported recently. But I would like to mostly focus on something that we've been leading, again, some in collaboration with Liang Feng, and that is, so I want to talk about two topics, but signal transmission using topological principles, and a quantum signal detection or signal detection, so a direct measurement of the orbital and spin angular momentum state on a chip. That's what we've been focusing on. So I'll mostly focus on the detector part. That's where a lot of very interesting physics is. And then there's a lot of very interesting stuff in topological polartonics that we've recently done. So time permitting, I'll move to that. But this is what I want to focus on. That is detection, direct detection on a chip of spin and different angular momentum states of light. That's a very, very difficult problem, and all throughout the path, at least the angular momentum part, people told me it cannot be done. So that so that's like a personal struggle I went through, including my student who worked on it. But yeah, eventually we prevailed and it worked out. So the effect at core, and I'll give you some introduction that enables us to do this, is what is called the photogalvanic effect. Okay. So just like in electrochemistry, and again, I'm a chemist, in my heart. So we have the galvanic effect, electrogalvanic effect, in which you take two chemical reactions with different redox potentials, you combine them through a salt bridge and an external circuitry, and you can drive current. So the potential difference that you create is the difference in the redox potentials of the two chemical reactions. And you can drive, if you put a load resistor, you can drive, you can extract current, and that's how our batteries work. So photovoltaics, the solar cells that we talk about are based on similar principle, but here you have a PN junction. So you basically break the symmetry of the system by creating a PN junction, and then if absorption takes place, there's separation of carriers at this interface. And then depending on the different chemical potential of the two materials, the carriers go in different directions. You create a photovoltage, and if you connect it to a load resistor, you can drive current, and that's how photovoltaic devices work. But so this regular photovoltaics or solar cells, it's a linear optical effect, and so you have to break a symmetry. So for many years, I mean, starting in 70s, I would say, and more recently, the term has been changed. Now it's called what is called bulk photovoltaic effect. So the idea is, can you get the same thing? Can you convert light to current without applying any external bias? So it's not a photo current type device. It's a photogalvanic, because in a galvanic effect or photogalvanic effect, you don't have to apply a bias to drive current. So current is spontaneously produced. So can you create photovoltaic effect in a bulk of the material without having such interfaces with break symmetry? So, and this is an intrinsically nonlinear effect, and this is very strongly governed by the optical polarization, both linear and circular. Okay. So a particular effect that I'll focus on, and that is because it's more robust to intrinsic parameters than its extrinsic parameters, is the circular photogalvanic effect, which is driven by circular polarization of light. So as I said, light has two fundamental polarization, left and right circular polarized states, which are related to the different photon spins at the quantum level. So the circular photogalvanic effect it's like a screw motion. So if we shine light with which is right circularly polarized light, and depending on the helicity of this screw, it either can move in one direction or the other direction. So if that happens, that means the system is chiral, but most strictly speaking, gyrotropic, and then you have this effect. So phenomenologically, this is basically given by this expression CPG, so circular photogalvanic effect, and the analog of this is linear photogalvanic effect, depending on the linear polarization, and this depends on E cross E star, which is basically nothing but the helicity of light. So so the E star is the complex conjugate of the optical field that you write, and this is governed by this tensor element beta ij, so nonlinear tensor. Okay, so helicity of light is plus if it is purely left circular polarized or right circular polarized light, it's plus or minus 1, and all intermediate states, fractional values of this helicity either give you elliptical states or linear polarization. So for most materials, beta ij is 0, but if it is non-zero, then E cross E star, which depends on the helicity of light, can produce a current, and E cross E star changes its sign plus or minus 1, and hence the current direction changes. So if you have this, if beta ij is non-zero, then you have this effect. And this effect was first, at least to the best of my knowledge, was reported, like most things in Russia and in 70s, on a crystal of tellurium. So the experiment is the following. At least the experiment that we do, and I'll take a moment to explain. So we come in with linearly polarized light, and we shine this light on a quarter wave plate along the long axis. So the output light is still linearly polarized, and then we rotate the quarter wave plate and produce different polarization states. So when the quarter wave long axis of the quarter wave plate is at 45 degrees, we produce left circularly polarized light, and at 135 degrees we produce the opposite helicity. And if the measured photocurrent is different at these two values, then there's a good chance we have this circular photogalvanic effect. But this also produces light of elliptical polarization and linear polarization, because we get back the linear polarization we start with at certain angles, 90 degrees, for example. So it has components of the linear photogalvanic effect, and that basically goes 4 times the rate at which we rotate the quarter wave plate. The circular polarization goes as twice that, from 0 to 360 degrees, and some background current. So if we just take the circular part, then it changes its sign. But of course, there's other types of phenomena. There's thermal current, which is typically not polarization sensitive. There's linear polarization dependent current. So all kinds of things can happen. So we have to extract that from these experiments. Okay. So the photogalvanic effect is a nonlinear effect. So one can expand the polarization. Once, if you shine light on a material, you polarize the material. So you can do a perturbative expansion, and that happens if the electric field is weaker than any of the interatomic or intermolecular forces that are acting on the system, or that are intrinsic to the system. So if you have much below that, then you can do a perturbative expansion of the polarization. So the linear term is given by chi1, or determined by chi1, which is the linear susceptibility, and it produces the linear effect like absorption, emission, fluorescence, and then the nonlinear term here. So the most common manifestation of this chi2 effect is, we all know, is some frequency generation or difference frequency generation. So in second harmonic generation, we have, if you have light of frequency omega and another optical field of omega with frequency omega 1 and omega 2, then you can create some and difference frequency generation. So that's the second harmonic generation or some frequency generation. But however, if the two interactions are with optical field with omega and minus omega, then you produce a DC field, and the manifestation of that is electric current, which is what we measure. And that is the origin of photogalvanic effect. So as you know, chi2 cannot happen in regular crystal, most regular crystals, so it has to have some symmetry breaking. So there are 18 point groups which are identified as gyrotropic, which can in principle produce this effect. So this is more or less a necessary condition, but I would like to point this out, and this is where most of the advances that we have done is so these 18 gyrotropic point groups enable this effect only within under the electric dipole approximation. That is, we assume that the dipole, the transition dipole of the material interacting with the optical field produces this response. But you can have, when you do a multipolar response expansion, you can get quadrupolar magnetic dipole and higher order responses, and that's when the requirement is not that stringent. Okay. So different mechanisms produce this photogalvanic effect. One is what is called the injection of current, where you inject carriers and then they relax. The other is what is called the shift current. There's a lot of interest here because it's a coherent response of the system, and that is because of the asymmetry in the electronic states of the initial and final states. The wave packet basically undergoes a spontaneous shift, and which produces this non-equilibrium states. And if you do a density matrix expansion, it's the off-diagonal elements of the density matrices, which basically are the coherent, which determine the coherences of the material, and the relaxation of these coherences, which produce this response. And the third response is what is called.
Ritesh, there is a question from Ajay Sood.
Oh, okay, sure.
I think. Yeah.
Hi, Ritesh.
Please go ahead.
Yeah, Ritesh, just a small clarification.
Sure.
Supposing you have a surface electric field, then you know that from chi3 also you can get the effect on second harmonic. So is it that that is not very large or important in your experiment?
So yeah, it's a very good question. So you can have all kinds of responses. Surface response can also be there. So if the response of the system is weak, when this bulk response by symmetry is not allowed, then we have to be very careful. If the bulk response is allowed, then the surface response typically tends to be at least 1 or 2 orders of magnitude smaller. But if the bulk response is not allowed and we have higher order effects, then we have to be very careful in describing the response. And we have then through symmetry analysis and through more detailed experiments, this is where the spectroscopy part come in. We have to eliminate the response from the bulk and the effects on the surface that you described. So it's a very good question.
Yeah, no, so I was just wondering that by design, supposing if you take on topological insulators where the surface states will make a big contribution, so it could be quite different from this bulk response. That's the question.
That's exactly how we started into this problem in 2000 with Sajal in 2012 or 13, and we we moved to other systems. Weyl semi-metals because specifically because they have a bulk, because all the topological states are in the bulk. And now after developing all these tools, we are now just starting to revisit this problem. Yeah, but I don't have the results because just starting, but that's exactly what we are now trying to do. I mean, it's complicated, as you rightly point out, and it's a work in progress.
Thank you.
Okay, so so we have injection current, which comes from symmetric relaxation of symmetric carrier relaxation. Symmetric carrier relaxation means if you go from K1 state to K2, the rate is tau. Then K2 to K1 is also tau. And then there's another relaxation mechanism of current, which is called the ballistic current, which comes from asymmetric carrier relaxation, which means if the rate of relaxation from K1 to K2 if is tau, then K2 to K1 is not tau. So that's asymmetric carrier relaxation, and that when that dominates, or when that part of the current is what is called ballistic current. So there are 3 mechanisms: injection, ballistic, and shift. So if we expand the photogalvanic effect, the total photogalvanic effect, including linear and circular, we can basically write, we can take the tensor element, the beta that I talked about, and create 2 different tensor elements based on the symmetricization and anti-symmetricization. So the anti-symmetric part of the tensor produces circular photogalvanic effect, and that's why it's more stringent in terms of symmetry requirements. And the symmetricized part of the tensor produces the linear photogalvanic effect. So that is why it is more prone to extrinsic effects, like scattering, electrodes, all kinds of things. So that's why we mostly focus on CPGE. Okay. So of late, because of the emergence of new systems, there's a lot of interest in circular photogalvanic effect. And as Professor Sood pointed out, there was a paper in 2011, which published in 2011, which probe this photogalvanic effect in bismuth selenide, a topological insulator. But there's a lot of, now people don't believe it's the interpretation is correct, because the frequency of light they were using was in the visible range, or 800 nanometers, close to visible range, and these surface states exist only in the mid-infrared range. So, but again, that was the beginning. So a few years back, I mean now almost half a decade, with Sajal, and collaboration with Jean Melee, we published a photogalvanic effect in silicon, and that was very surprising because silicon has all the. It's not a gyrotropic point group. It has, it's a diamond structure, and it has all the mirror symmetries. But still, we were able to measure photogalvanic effect in silicon, and that was because of the presence of Schottky field. Symmetry was getting broken. It was, and it was also because of these linear chain surface states on silicon, and doing spectroscopy and the photogalvanic experiments. Sajal was able to show that this comes from the surface states of silicon. So point here is, in the presence of electric field and the surface states, unique surface states, we break all the symmetries in this material, and we render the material gyrotropic, and we produce this effect. So that's how we got started. But the reason why we got started is because we were doing, at that time we didn't know about this paper. So we were doing on bismuth selenide, and we were not sure if the effect was coming from surface or bulk. These people were more bold, so they published what they got. but we did not, thankfully. And then we decided to do one experiment on silicon because silicon should not have this effect. Yeah. So we, Sajal said, okay, I'll go in on Saturday or Sunday. Pavan, I think, has probably more stories about Sajal, but yeah. So he went in over the weekend and then started to report that even silicon has this effect. So that scared us. It was like something is wrong. So we spent 3 years figuring out this problem in silicon, and then first, most of the time to make sure that the experiments were not wrong, and then what it meant. So it produced a very interesting paper. It was published a while back. So that's how we got started. So before I get into the measurements on a particular topological material, Weyl semi-metal. So a very, very brief introduction to the role of topology in condensed matter systems. Most of you probably know, just know more than I do. It's for people who may not have much experience like me a few years back, just 3-4 years back. So the idea of topology in condensed matter systems really became central because of this experiment called the quantum Hall effect. So in quantum Hall effect, it's like a Hall effect, but under very strong fields in two-dimensional electron gases. So the transverse current, if you apply voltage in one direction in the presence of strong magnetic field, and if you measure transverse current, what was surprising was the emergence of these conductance plateaus. So this probably is a picture from fractional quantum Hall effect, which is another advanced experiment from integral quantum Hall effect. But nevertheless, these plateaus. What was interesting was, and what people could not explain, but they knew they had figured out something interesting, before theorists helped them, was that these conductance plateaus were highly quantized, and if we change the state of the system, like for example, change the disorder in the material, or do other things, these conductance plateaus would not change. So this could not be explained by regular transport theory, because if you change the state of disorder in the system, transport changes, but these conductance plateaus did not. So that basically brought out the idea that there must be something different, and this is where the idea of topology, which makes the system more robust, came into being. And then people started to appreciate the role of topology in the system, and from topology, the most important thing is the emergence of these topological invariants, which describe the topological state of the system. And depending on the type of system or dimensionality of the system, there are different invariants, like the Zach phase, winding number, Chern number, more recently Z2 in topological insulators. But importantly, another important concept that emerged was when you have these conductance plateaus, then the transport is along the edges of the sample. But the properties of this transport, the edge transport, is determined by the bulk, so which is related by these topological invariants, and hence the bulk edge correspondence. So these are the ideas that emerged from the quantum Hall effect. And so in a quantum Hall effect, as you know, you apply a very strong magnetic field, so you break the time reversal symmetry of the system, and you get this response. So one of the biggest breakthroughs of my colleagues, Charlie Kane and Jean Meillet, was they realized another type of topological system without applying any magnetic field. So, and this is what is called a topological insulator, and the invariant is called the Z2 invariant. So so again, this is a chemist or quantum chemist perspective of a topological theory, and actually this works very nicely. So in a non-topological crystalline system, let's say cadmium sulfide, one has a particular ordering of bands, and you have the valence band. In cadmium sulfide, it is mostly determined by, at least at the gamma point, by p orbitals, and the conduction band by s orbitals. So that is what is called the normal ordering of the bands, and that is, let's say, it's defined by a topological invariant. It is a trivial insulator, so the invariant is 0. The Z2 invariant is 0. However, if you introduce very strong spin orbit coupling, and the spin orbit coupling becomes much more than the band gap of the material, then you can mess up the ordering of the bands, and then the conduction band can actually come below the valence band, and you can have very interesting band crossings. Those band crossings can be predicted. So it's not that band crossings didn't. Chemists and physicists have known band crossings. It's where they occur. So if they occur close to the Fermi level, then they can they can be probed. And, so so the idea what I'm describing, where the conduction band goes below the valence band, is what is called roughly called band inversion, and this is a hallmark of topological systems. So when you have in a material, if you have this type of inversion of bands, and of course you have to have certain symmetries which protect those states, then the topological invariant changes. So now you have two different insulators, and with two different topological invariants, then any adiabatic perturbation cannot take you from one state to the other. The only way you can go from one Hamiltonian of one insulator to the other with a different topological invariant is by closing a gap. So that's what these people figured out. So if you have an interface between a material with a non-zero topological invariant, let's say Z2 is 1 for a material like bismuth selenide, and its interface with some other material or vacuum, which is a trivial insulator, then since these two insulators have a different Z2 invariant, then at the interface the band has to close, which means at the surface of this material you will have a closed band gap system, which means that on the surface you have metallic states. And these metallic states and this crossing, they're protected by time reversal symmetry because you don't apply any magnetic field. So you can think of this system as two copies of the quantum Hall effect, but with spin momentum locking. And this spin momentum locking basically is emergence of spin orbits, very strong spin orbit coupling. So now the edge states become spin polarized, these are states with the spin and momentum locked. So you have one state with spin up going in clockwise direction, and the other state with the spin down going in the anti-clockwise direction. So here, as Professor Su rightly pointed out, you have these states only on the surface of the topological insulator. And initially samples made of bismuth selenide had a lot of problems. Now I think there's a lot of progress that has been made, where the Fermi level of the material would go into the conduction band, and then the surface and bulk could not be disentangled easily. So a few years back, a very important breakthrough occurred in condensed matter, and this was actually done by my classmate from Kanpur, Ashwin, who's at Harvard now. So he basically figured out that you can have, again, particle physics analogs of in condensed matter, what are called Weyl semimetals, where because of some in the bulk you can have these band crossings, and because of this very unique combination of spin polymatrices, once you create this crossing in the bulk, you cannot remove these crossings, so they become topologically protected. So now these crossings occur in the bulk and they're protected. So that basically means you can have these very interesting states in the bulk. Of course, on the surface, you can have these what are called these Fermi arcs, which I won't talk about. But so this is a Weyl semimetal. So there are two types of Weyl semimetals. So to think about the Weyl semimetal is you start with the Dirac semimetal, just like graphene in 2 dimensions, but these are 3-dimensional Dirac semimetals, and cadmium arsenide is one example of a Dirac semimetal. And if you break certain symmetries, time or inversion symmetry, then you can create 2 copies of this Dirac semimetal, which are called Dirac cones, which are called Weyl cones, and they carry opposite chiralities. So the low energy excitations here, which are called Weyl fermions, have different chirality, and depending on which particular direction these crossings occur in K-space, if they occur in very weird directions, very low symmetry points, then these Dirac cones could be very heavily tilted, and there you can create electron and hole pockets. But at the interface of these electron and hole pockets, you can create these topological states. So these are called type 2 Weyl semimetals. So there was some work around the time we published on this circular photographic effect in Weyl semimetals. So clearly there's a lot of interest, but I'll get to what we have. So the material that we worked on is these layered material MOTE2 or tungsten doped MOTE2. So in the high temperature phase, it's a semi-metal, but in 1T prime phase, which is inversion symmetric. So it's a trivial semi-metal. But if you lower the temperature, so in MOTE2, I think this is around 270 Kelvin or so, then you have people call it topological phase transition. It's a structural phase transition going from T prime, 1T prime to TD, and then it becomes a Weyl semi-metal. That's what people thought, but Zaid Hassan's group and other groups did RPES on this and proved that there is, indeed you have a Weyl crossings in these materials, and structurally it showed phase transitions. People did Raman spectroscopy, so convention characterization of these materials. So, but another way is you start with MOT2, and if you dope it with enough tungsten, I think 30% or so, then you can have this Weyl semi-metal state at room temperature. So you can have this quantum response, a quantum state of a material at room temperature. So this was very exciting. So we got the same material from Zheng Liu, who had from the same growth given this material to Zahid Hassan, and who had done ARPUS characterization. So we know for sure, we have to start with a material where it has been pretty nicely characterized. So we got the crystals on the same batch of growth. So, and then we did this circular photogalvanic effect. We started off from different hypotheses, and of course, like most experiments, ended up on a different path. But that's the journey that I'm going to describe now. Okay. So here's the experiment. So these materials, okay, let's say MOT2. So if you do it at room temperature, it's 1T prime, non-Weyl semi-metal, inversion symmetric phase. So it basically, it's a layered material along C-axis. So we exfoliate this material and we shine light at normal incidence. So this material has two mirror planes, let's say X and Y direction. So this is the geometry of the experiment. We shine light, and this material should not produce circular photogalvanic effect. Even if the inversion symmetry is broken, because on the crystal facet that we shine light on at normal incidence, the two mirror planes will cancel the response. Okay, so and anyways, we still did the experiment. Now I can't remember why. Yeah. If sometimes I think, as a very good example I give to students, sometimes it is good just to do things. Sometimes it is good to not know everything, because if I knew what I know now, I mean not know this, but if I had done all the symmetry analysis very carefully, or if my student had done it, we would not have done this experiment because the response would have been 0. So yeah, we still did it. So here's the experiment. So these are a bunch of electrodes which are not biased. We just measure current through these electrodes. And if we shine light on one particular, on one particular side, let's say here, in 1T prime phase, there is no circular photogalvanic effect. 45 and 135 degrees produce the same response. But keeping everything else the same, if we take the material through a transition, phase transition, so lower the temperature, and we do the same experiment, you can now see circular photogalvanic effect builds up. So left and right circularly polarized light produces different response. Okay, so that was exciting. Okay, then we did an experiment on the other, so on the mirror symmetric side. So basically on this side, where my pointer is, so shine here. And we did the same experiment, 1T prime, no response. But in the TD phase, in the inversion broken phase, the response was there, but the phase of the response was different. So something had changed, and it's a very strong function of where we excite. So we did an experiment where we basically scanned the laser from one side to the other side, and we measured the circular photogalvanic effect. So when we are far away from this from the electrodes, then the response is 0. And as we approach, so this basically we are moving along the line joining the two electrodes, so the bisector of the two electrodes, line joining the electrodes. So as we start to move towards the center of the two electrodes, then the response starts to build up, and then it starts to decrease. When we reach the center, then the response goes to 0. And one can think from very symmetry analysis, basic symmetry analysis, when we have the center of the two electrodes, then we don't break any symmetry by light, spatial symmetry by light. So that makes sense. And then when we go to the other side, the response basically flips its sign, so it becomes negative. So clearly there's a very strong spatial inhomogeneity. So our light is focused, not super tightly focused, but focused to a few micron spot size. So then we basically fix the laser spot at one point, and we change the focus of the light, of the size of the beam. And then when the beam is very, very small, very large, so in the plane wave limit, the response goes to 0. And as we focus the beam tightly, then the response basically starts to build up. So it's clearly showing that this is an inhomogeneous effect, which depends on the state of the spatial state of the beam. So it cannot be obtained in the limit of a plane wave excitation. And that actually is true. And that's exactly the reason why we should not have done the experiment. That is because in the direction in which we are coming, in the crystal facet that we are hitting, it has two mirror plane symmetries. So under plane wave approximation, or simply speaking, the electric dipole approximation of light matter interaction, this effect should be 0. But when we focus this light, the response emerges. So all these spatial inhomogeneous effects, if you combine it together, what is really happening is when we shine right circularly polarized light, the photocurrent basically swirls in one particular direction. So this is slightly complicated because now instead of photocurrent going linearly in a particular direction, it actually circulates. So right circularly polarized light produces photocurrent that circulates in the clockwise direction. And if you change the helicity of light, make it anti-clockwise, or left circularly polarized, then the photocurrent swirls in the anti-clockwise direction. That's what it means. So it's a very interesting effect, and it's a pretty strong effect. So we needed some help from the theorists. So this is where Zorun collaborated very closely with Charlie Kane and Jean Meillet, and under their guidance developed a microscopic response theory to explain this effect. So the complication here is the following. Most condensed matter theories, you solve it in K-space because spatially you have mostly things which are homogeneous. But now if you have phenomena which is determined by the inhomogeneous state of light, spatially inhomogeneous light, then you have to have information of both real space and K-space. And this is where you have to, theory becomes slightly complicated. You have to use Wigner transformation, which carries in information under some compromises of both real and K-space. And this is what she used to derive the response functions. But phenomenologically, which is what we did before we went to the theorists. So as I said, the regular photogalvanic effect comes from this E cross E star response, which is the helicity of light. But now when we focus light into a Gaussian beam, and if you do a Fourier transform, it basically produces an in-plane momentum, which is determined by the focusing condition of the light. So now this Q, in-plane Q, which is pointing in the radial direction because it's a Gaussian beam, it's crossed with E cross E star, and that basically produces this circular response because of this cross product. But what this also means is, and this we can see also in real space information, when we shine at the center of the two electrodes, the response goes away. But it comes back when we shine on the other sides, where we break certain symmetries, which basically means in K-space, this effect requires asymmetric excitation of carriers in K-space. So plus K and minus K carrier densities or transition densities that we create should be different. Otherwise, this term would be zero, which is exactly what happens when we shine at the line joining the two electrodes. So as I said, this response comes from the field gradient, intensity gradient, which some of you may know very quick, easily. It's in very basic, it's in all spectroscopy books.
Ritesh, just to interrupt,
sure.
About 10 minutes for the talk.
Okay, sure. I think I won't be able to talk about the other thing, but that's fine. So this basically comes from the field gradient. So it's a non-local response because in a local response, you have a response which is only determined by the local field intensity or local field. So that is why the phase information is lost and all other information is lost. But here the response comes from the field gradient. So it's a non-local response and it requires either electric quadrupole or magnetic dipole interactions. So here is the response, microscopic response function that Zorun developed with the theorists. So starting with the quantum kinetic equation with Alan McDonald had developed just a few, while we were doing the experiments, pretty much. So this is the response function. So because of this Q wave vector, which comes from the intensity gradient, this becomes an electric quadrupole or magnetic dipole type response. So there are a couple of differences here. One important difference here is a regular electric dipole response, a conventional CPG, is linear in the band velocities, but this SCPG or spatially dispersive CPG is quadratic with band velocities, and that has profound effects. And this is a term which for a two-band system collapses into what is called the Berry curvature of the system, and these are relaxation parameters of the system. So upon symmetry analysis, what we found was something very interesting, and that is the response is non-zero only if we have asymmetric scattering, or in other words, whatever response we measure only measures the ballistic current of the system. And this is one of the very few spectroscopic techniques or technique which can directly measure in some form the asymmetric carrier relaxation rates. So that comes from symmetry relaxation, symmetry analysis, and which basically justifies why you need response function type analysis to understand the system. And to prove that this comes from asymmetric carrier relaxation. So if we do an experiment as a function of temperature, so as we lower the temperature, the the phonon scattering, which basically follow the same symmetry principles, they get frozen. So asymmetric carrier relaxation is kind of, the rate should be diminished, and that's exactly what happens. If we do an experiment at lower temperatures, the circular photogalvanic response actually decreased, which basically shows that the phonon asymmetric carrier relaxation from phonons are important. Okay, so so as of now, I described the experiment at very high frequencies, but showed the effect, which was mostly governed by symmetry principles. Then we started to do the experiment in the mid-IR range, where we excite actually close in the region where the Weyl cones exist, so the dispersion is linear. So we excite Weyl fermions from the valence to the conduction band, and we found a very strong CPG response. In fact, the response is around 10 times or 20 times strong, order of magnitude stronger, and that is because the Berry curvature in the vicinity of the Weyl cone is very, very large. So at the Weyl crossing, the Berry curvature has a singularity, so 1 by k cube, so it goes through a singularity at k cube, at that 0 point. But in the vicinity, the Weyl curve, the Berry curvature is has very large value. So by doing this experiment, our experimental probe is basically sensitive to Berry curvature of the system also. But here comes the kicker, which was very exciting. So as I said, if I do an experiment where I shine light at this point A, and I shine it at high frequencies in the visible range, let's say, I shine light which is right circularly polarized, so I get photocurrent which circulates clockwise. Okay, so now I keep everything the same spot size, same spot, same everything, and if we only change the polarization state of light. Okay, so I shine low frequency light, let's say 6 micron mid IR in the Weyl cone, but polarization is different, left circularly polarized light. What we found was very surprising. The photocurrent swirling direction changed, so not by polarization, but just by changing the frequency of light. So what is happening? So the reason lies in band inversion. So in the region of Weyl cone, we have band inversion. That's how these systems are characterized. So why is this response sensitive? So here's the explanation. So in a conventional photogalvanic effect, as I said, there's a term which mirrors the Berry curvature. And you have a response which is linear to band velocity. Okay, so in the band inversion region, both omega and v band velocity change sign, so the net response does not change sign. But in our response, in the spatially dispersive photogalvanic effect, we have a response which is quadratic with the band velocity. So Berry curvature changes sign in the inverted region, but the band velocities also change sign, but it's quadratic, so the response becomes negative. So now we have a technique which is also sensitive, in addition to sensitive to being to asymmetric carrier relaxation, Berry curvature, of course, symmetries, a response which is also sensitive to band curvature, band inversion, which is a hallmark of topological systems. Okay, so a good question to ask was, at some frequencies you have a circular photogalvanic effect which is characterized by plus sign, let's say right swirling in the clockwise direction. At some frequencies, it's characterized by the opposite. Swirling. So so at some point the circular photogalvanic response must cancel to 0. So Zoran did a beautiful experiment, and very hard experiment, keeping everything the same. She scanned from visible to the mid IR range, which means many different laser systems. She was able to characterize the point at which this response goes to 0 and flips its sign. And by combining DFT calculations, which again she did, so she can do almost everything, what she showed was the frequency at which this response goes to 0 is very sensitive to the average asymmetric carrier relaxation. And from there, we were able to also extract, this is what spectroscopists do, and this is where my core in physical chemistry comes in. We were able to extract this average asymmetric carrier relaxation time. So some people may, I would like to point out that in the moment you start talking about asymmetric or symmetric carrier relaxation, you've basically gone beyond. This basically means you have basically gone beyond the relaxation approximation Boltzmann theory. So this is already going beyond the relaxation time approximation approach. So this is basically making our analysis more complex, and we can extract more information. So before in 2 minutes I show you the OAM part, which is how I started. I just want to show that what we have is a tool, a spectroscopic tool, where we can extract a lot of information about the symmetry of the system, Berry curvature of the system, and also the band inversion topology and the relaxation, some parameters of relaxation kinetics or dynamics of the system. All right, so in 2 minutes, I'll quickly go through this part. So, okay, when Sajal was doing these experiments on silicon, we knew that we have a detector that is sensitive to photon spin. Okay, so, but then I had some experience with dealing with OAM light as a postdoc. With David Greer, I was doing optical trapping and swirling nanowires with OAM light. So I always had this thing: can we detect directly this orbital angular momentum mode of light directly in a photodetector? And the answer is no. And the answer is no because the information of the orbital angular momentum mode lies in the phase of light. Okay, so here this is the electric field of OAM light. So the phase of light basically swirls in the azimuthal direction, and this is given by this function Im e to the power Im phi, where phi is the azimuthal angle and m is the quantum number of that light. So this is where the information is. So if you have a regular photodetector, like most photodetectors, the response is local, and this phase information is lost. Okay, but the moment I started to see this data on this circular photograph, spatially dispersive CPG, where the response was sensitive to the intensity gradients, I started getting excited. Maybe there is a way. So if we are sensitive to intensity gradients, we should be also sensitive to the phase gradient, because the only thing that has changed is we have a wave in the Gaussian beam. We have a wave vector which is in the radial direction. Now we have a wave vector which is going in the azimuthal direction. Okay, so that's the only thing. So can we detect that? If we can detect, then we can detect the orbital photogalvanic effect. We can detect the orbital angular momentum mode. And the corresponding photogalvanic effect, we just named it orbital photogalvanic effect.
So Ritesh,
yeah,
your voice is not audible.
Oh, can you hear me now?
It is audible. It is audible.
Yeah, please continue.
So yeah, so so that was the question: can we detect the orbital of the phase? So that clearly meant we have to go beyond the electric dipole approximation and extract the phase information. So we need, so while semimetals turn out to be the one of the best materials, because under normal incidence, the electric dipole term is 0 by symmetry, because it has two mirror terms, mirror symmetries. So yeah, we can go to the non-local response, and that's exactly what we did. So phenomenologically, now we have a microscopic theory. So if we write the DC photogalvanic effect response in the presence of both intensity and phase information of light gradients. So this is the electric dipole term. So as you can see, it only determined by the electric field, and it gets cancelled. The phase information gets cancelled. But the other higher order terms, the electric quadrupole and magnetic dipole terms, they depend on the electric field gradient. And then you can extract that, which I talked about in the first part of my talk for intensity gradients. And this other term is sensitive to phase gradients. So that's the experiment. So the only difference, as you saw previously, in the intensity gradient case, we have a wave vector which is in the radial direction, and when it is crossed with the helicity of light, the photocurrent swirls, either clockwise or anti-clockwise. Now, if we have the wave vector which is swirling in this direction, so azimuthal wave vector that is produced because of the phase gradient, then the photocurrent should be radial. Okay, so how do we pick it? So pick this up. So we designed electrodes which are radial in symmetry. So between the two electrodes, if there is this radial current coming from this azimuthal phase gradient, then we should be able to pick it up. And indeed, we were able to pick this up. And by changing the orbital, by changing the topological state of light, so basically m, so m equal to 1, 2, 3, 4, or -1, -2, -3, we were able to extract this information directly in one shot. And interestingly, is what we found was, and again it makes sense, the response is discretized by this orbital angular momentum mode of light. So if m is 0, then response is 0. M is 1, 2, 3, 4. It basically scales with all the parameters which are determined by the geometry of the system. So if it is plus, then we go in plus direction. If it is minus, we go in minus direction. And of course, it makes sense because the wave vector, the azimuthal wave vector will change its sign. So the direction of the radial photocurrent will change. So what we have here is a total photocurrent, which is determined by m, which is given by the orbital angular momentum mode of light, and sigma, which is the spin which is polarization of light. So m dot sigma. M dot sigma is the topological winding number of light, total topological winding number of light. So what we have is basically, in some ways, is topological light interacting with topological semimetals. And the phenomena is what we call the orbital photogalvanic effect. And we believe in these Weyl cones, or even in topological insulators, by transferring this orbital angular momentum mode to carriers, and if you have a linear dispersion, as you have in Weyl cones, we should be able to create these swirling charge vortices also. It's one of the things that we have dreams about, so we'll see what happens. But important thing is now we have a detector which is sensitive to the total topological winding number of light. So what does this translate to? Our detectors is sensitive to the orbital angular momentum mode and spin angular momentum mode, or spin angular momentum of light. If we couple these two, then the total state of light is given by what is called the point carrier sphere, and each point in the point carrier sphere is corresponding to a particular orbital angular momentum state and spin angular momentum state. Since our detector is sensitive to both, we basically showed, without getting into the details, that indeed we can measure unique photocurrents coming from different spin and angular momentum states of light. So what we have is, in other words, we have a detector which is sensitive to all these things. So again, I will not talk about all these things. So in short, what we have is, so this is, by engineering the state of light, by intensity gradient engineering or phase gradient engineering, what we are developing are local and non-local photocurrent spectroscopies to probe the band structure topology and even carrier dynamics of light. Symmetry is, of course, symmetry is the first thing that comes out. And so we are developing all these types of different spectroscopies and using different frequencies of light, different polarization or angular momentum states of light. Our idea is to be able to completely characterize the low energy band structures of these materials and disentangle all these different effects and start to make sense of all these things. Okay, so what I will not talk about is, I'll go to my last slide. I knew I will not be able to go through this. Okay, so I'll go backwards. Okay, so in short, what we have is, what I want to circle back to where I started. So we have shown on-chip light sources, which can produce different OAM and spin angular momentum states of light. What I didn't talk about is our recent work on topological polaritons, where we can, using a topological insulator equivalent of polaritons. So it's a quantum spin Hall effect of polaritons. Polaritons are light matter coupled systems, very strong coupling between light and the optical cavity modes. We showed that we can create these topological polaritons. But what I focused mostly on was these detectors that can detect directly the spin and orbital angular momentum state of light. And so this is where we are. So now we have designs for, so okay, can we do a single photon detection of, can we take the detector to the quantum limit and detect single photons? So we have a design now, but what we have to do is we have to take it to a superconducting phase, take the Weyl semimetal to the superconducting state. It will still maintain the same symmetries. So our hope is by creating these spatial pattern of electrodes to be able to detect single photon spin and orbital angular momentum states. Will it happen or not? I don't know, but hope is it will. And then we have some design criteria, and this is the motivation of my talk, to create a hyperentangled state. So one is regular entanglement between the different polarization of the photon. But if you add another degree of freedom, which is the orbital angular momentum mode, then you can create hyperentangled photon pair states, hyperentanglement between two photons in different spin and orbital angular momentum states. So by doing this, one can encode more quantum information in the optical networks. And this is what we're working with Liang Feng, my colleague. I'm working from the detector side with the idea of, in single shot, can we detect the state of a photon, single photon, and then in the future, if we can do that, can we detect the hyperentangled photon states, and then push these things to the quantum regime. So yeah, so this is where I end, and the idea here, the basic idea is these are mostly fundamental studies. That's what I am. By no means I do anything applied. So by understanding and engineering light matter interactions across different length scales, different materials, combining now ideas of geometry and topology, we are trying to learn new things and hopefully use this toolkit to make new device protocols for the future chiral quantum infrastructure. So with this, I end my talk, and I thank you all for your attention, and I thank all my group members and the funding agencies for their support. So thank you very much.
Thanks, Ritesh, for the wonderful talk. I'm sure everybody enjoyed it. Okay, Arindam has a question. Arindam, please go ahead.
Can you hear, Ritesh?
Yes, yes.
Okay, good. Great talk, man. So, quick question regarding when you just said at the end that you need to go through the superconductivity route. Is it possible to create these kind of materials through proximity-induced engineering? For example, whether one should be, proximity couple a layer of graphene, for example, with say something which has got a strong spin orbit interaction, like not MOTE2 per se, but if you take a look at the tungsten selenide and things like that. So can one introduce a spin orbit coupling where the light matter interaction can be created in the entangled zone that you just said?
So one thing is, it has to have certain symmetry constraints because, so the material you said, if you come, the direction in which the light is coming, the electric dipole term should be 0. So if it has the right mirror symmetries which cancel that effect, that's important. Then non-linearity should be very large to be able to detect this. So this is where Weyl semimetals, all these topological materials, people are trying to understand. There's some level of understanding which they have very large non-linearities. Some people claim it's 1,000 times. So in principle, if it has the right symmetry, okay, so at least the orbital OM part, we have not used any topological properties yet. That would be the next. So what if it satisfies the right symmetry requirements, and then I think in this proximity effect that you're talking about, I see no reason why it should not work.
Right.
As long as those requirements.
Yeah, just before Ajay asks, the reason I ask the question is now these van der Waals heterostructures are becoming quite interesting, and you can actually couple two materials. Even if you look at the materials with WS2, WSC2, where you create excitons which are topological in nature by themselves. So you start the material itself; it's very different from a bulk material like molybdenum telluride or something of that sort. So how much of entire work that you just showed can be engineered in such hybrid structures? That's what I was trying to get at.
I mean, as I said, I see no reason why it cannot be done, as long as the engineered system produces those type of symmetries that are required. So in principle, it should be done. And maybe you can engineer a much stronger response. So it's hard to say, but I see no reason why it cannot be done.
Great. Maybe we should talk when you're here.
Definitely. Yeah.
Okay, Ajay, please go ahead with your question.
Okay. Hi, Ritesh. Wonderful talk. I really enjoyed it. I just was last part, which you went little hurriedly, OAM part. Is that done in the TD state or is it done in the 1T prime stage? I missed that point because it will make a difference.
Yes, so it's a really good question. And this question should have been answered in the first part of the talk itself. When I was doing just the intensity gradient part. So okay. So the core of the question, if I understand correctly, is the 1T prime phase has inversion symmetry.
Yeah. Right.
TD phase has inversion symmetry, is inversion broken. The response that I'm describing, the spatial part, breaks symmetries because clearly when we shine at the line joining the two electrodes, the response goes to 0. When we shine away from it, the symmetry is broken. So what is the need for this inversion symmetry breaking? Right? I think that's the core of the question that you're asking. So,
right.
So exactly, and this is a really great question, and the answer lies in the response functions. So when we write the response function, and this insight could not have come. So if we had not done the response function part, I would have said it should work. But clearly, when I showed the data for 1T prime phase and TD phase for the spatially inhomogeneous for the SCPG part, intensity part. In 1T prime phase, the response was small or non-measurable, right? And then the TD phase, CPG was there. Okay, but symmetry requirements, a phenomenological model should predict that both phases should produce the response. So answer lies in when we write down the microscopic response. So the response function that corresponds to the TD phase, inversion broken phase, versus the non-inversion symmetry broken phase. The inversion broken part, in the inversion broken phase, the response function has a resonant term. So it basically scales as 1 by omega. But in the TD, in the 1T prime phase, where the inversion is not broken, the part that produces this response, the response produces non-resonant type response function. So it scales as 1 by omega square, if I'm correct. So that makes that response very weak. So that is why if you do a very, very sensitive measurement, the response is there in the 1T prime phase. It's just that it's very hard to measure. So then extending to OM phase, we did this in the TD phase because the response is much stronger.
Got it. If nobody, I'll ask one more question.
Sure.
Akshay, is that allowed?
Of course, Ajay, please go ahead.
Okay. No, my other point, which probably is very ill-conceived, but I was just thinking, now supposing you take monolayer MOS2, where we have the valley polarization. And now I know that when I do right circular or left circular, and if I do it in resonance, I know that I'll have the valley polarization. So will that also make an interesting difference in your response for the first part or even the second part? So I'm replacing my topological insulator, this Weyl cones, with a 2D material, but which has this valley polarization.
So you're talking about the experiment that the Skinfire Mark and Paul McEwen reported, I think, few years back, right?
Oh, I don't know. I have zero knowledge.
Okay, yes. So yes, you're right. So what they showed was they took, I don't know, WS2 or MOS2, and then they basically exposed this to circular polarized light, and they did a photon Hall effect type measurement. So they applied field in one direction and measured the photo response in the transverse direction, and then they did, as a function of applied voltage, they saw the transverse photocurrent increase. So and by changing the polarization of light, the response flipped. So they call it, I think, the valley Hall of photon valley Hall effect. I don't know, something along those lines. And when they went to a bilayer, this response was very small. It was there. So the reason why this response happens and the reason why it is different from my thing is, in MOS2 or WS2, at least in these crystals, they have the two mirror planes, which under normal incidence does not produce this response. So that is why they had to do this valley Hall of, they had to apply a transverse field because it broke a mirror symmetry. Circular polarization breaks time reversal symmetry. So you break all these two and you get this photon Hall effect type measurement.
Oh, thank you. Yeah, great. Thank you. Very nice talk.
Oh, thank you.
Okay, are there more questions? Maybe from any students that still exist on this talk?
Thanks.
Okay, Amlan, please go ahead.
Yeah, thank you. It was an excellent talk, Professor Agarwal. I have been following your work since a long time, and it is excellent that I see right now a direct orbital angular momentum detection. Very exciting. My question is rather very stupid, perhaps. How important are these electrodes? If I remove these electrons, do I still have, when I shine on these materials, circularly polarized light, do I still get swirling photocurrent? And if I did so, what is the order of magnitude, let's say, of this photocurrent and perhaps the magnetic field? And so one of the things that I could think of when you said superconducting material which is still have this symmetry, and then you could perhaps think of a spin qubit out of it. Is that? Yeah, this is what I'm asking.
Okay, so the first question is a really good question. Okay, let's go crazy. So yeah, I mean, time is not an issue now because the official part of the talk is over. Okay, it has to slow down, or I have to slow down. All right, so here, this is where your question is important. Okay, so as I said, when we shine light, which is focused, it produces this response, right? And then when the spot is small, then it produces a very strong circular photogalvanic effect. When the spot is large, so we approach the homogeneous excitation limit, plane wave limit, response goes to 0. But this is with respect to something, and that respect to something is the external geometry that we impose, that is the electrodes. So everything is related to how far are the electrodes. So yes, if my spot size is much bigger than, a rough length scale here is the electrode separation, then I reach the other limit and the response goes to, becomes very small. And in the other limit, I can make the spot size, of course, not experimentally, but in principle, arbitrarily small. Then what happens is the photocurrent circulates, and if the electrode separation is large, I won't be able to collect that current easily. Then, then I may miss that response. So what is hard to measure, but you can see some plateauing. Eventually, as we make the spot size smaller and smaller, there should be a turnover. It should decrease, and that is because electrode separation is probably much bigger than the spot size, because of which we are not able to collect the signal which is swirling. Okay, and as you can see, this is also, there's some asymmetry required here, because if I shine at the center of the two electrodes, then the potential that is developed in the two electrodes, I mean, you can write some very basic equations. We have that in the supplementary information. Then the current goes to 0, right? So if you're slightly off, then these two electrodes, you create different potentials, chemical potentials, and which produces this photocurrent that is measurable. So yeah, so everything, the relevant length scale here is the electrode separation. So how big is the spot compared to the electrode separation? That's the answer. And you may have to repeat the second part of the question. If I answered,
yeah, I understood that. Yeah, so what if I totally remove, the interesting question is, if I totally remove the electrodes and try to detect it in some other sense, let's say a magnetic field that is generated by this swirling current, what would the magnitude of that?
Another really good question. So we've not thought about this magnetic field, but another analog of this experiment is, what people do is they shine a femtosecond laser pulse on the sample, and they measure terahertz emission. So the terahertz, and this effect is basically the same photogalvanic effect, because you shine a femtosecond laser pulse, it has a pulse width. So you can have two interactions at omega-1 and omega-2, and the difference of this is in the terahertz, because in the envelope of the frequency envelope of the optical pulse, you can have different combinations of omegas which are in the terahertz range, and that, if the two omegas are exactly 0, we get a DC response. That's what we measure. Okay, so people measure terahertz emission. So, but typically what they do is, so yes, the material doesn't know that there are electrodes. It should not know. That's just our issue. So if I were to shine focused light on a material without electrodes, the current will still circulate. It's just that no one knows. No one would know that the current is circulating, or it's producing this response. So if I do a terahertz, people do terahertz emission and extract the same information that I'm talking about. But what they don't do is they just measure the total intensity of the pulse that comes out. So if they can do a spatially sensitive terahertz detection, right? So if they have a CCD, and I don't know if CCD for terahertz exists, maybe that's why they don't do it. Then they probably have to use an array of detectors or make up this experiment, complicate this experiment. Then this information should be there, because the terahertz emission at different regions on the sample, which is where the femtosecond pulse is exciting the sample, will be different, and then you can extract the same response. So it can be done. You're right. It's just that it gets very complicated. Current is easier to measure.
Yes, yes, definitely. Thank you. The last question was actually a bit exploratory. That suppose this is now a superconducting material. Now, for a short time, if you just have a pulse and you've just generated a swirling photocurrent, then it will be there forever, and it can be used as a spin qubit. Your thoughts on that?
In principle, yes. In principle, yes. I've not thought about this, but in principle, yes. You're right. But I don't know how it's going to manifest. I mean, frankly speaking, I'm not. I mean, I have I have a very vague knowledge of. Just like 3 years back, I had no knowledge of topological physics. I still don't have much idea, but I have some working knowledge. I'm in a state today where I don't know anything about superconductivity, pretty much except for very basic things at very basic level. So my answer could be wrong, but I think you probably are right. That can probably produce a current which can persist for some time, and then and then that probably can be measured, or something can happen there, and it can be a magnetic probe or some other probe, and then maybe some qubit type information can be encoded. Possible.
Thank you, Professor. It was so nice.
But maybe in 3 years from now, I'll be able to answer if we find something, and if I learn more about superconductivity.
Great.
Okay, any more questions from Ritesh? So one thing that people might not know, so we will just have some informal discussions. You can hang around or you can leave whatever you want. But let's thank Ritesh again for the wonderful talk and the patient question and answers. So thanks, Ritesh.
Thank you. Thanks for the invitation.
Thanks a lot, Ritesh. Thanks for your talk.